Hello everybody, we're going to get started here with section 14.1, functions of several variables. And so if we look here, I'll start with the definition. Suppose D is a set of n tuples of real numbers, x1, x2, so on up through xn. A real valued function f on D is a rule that assigns a unique single real number. So in other words, what we're saying is we're going to give it some input values, we're going to follow a rule, and it's going to map us to a single real output number to each element in D. And that real output number is, we're going to call that W. So we'll have a function of multiple variables that maps us to a value W. The set D is the function's domain. The set of W values taken on F is the function's range. And the symbol W is the dependent variable. It depends on what you pick. And then it's the function of independent variables, x1 all the way through xn. We also call the xj's the function's input variables and output variables for W. So we input stuff and it outputs it for us. So it's just a way to map several numbers to one number. We've seen something like this before when we did three-dimensional graphing, x, y, and z. We would input x and y and map us out a z. So we've already seen something like this. We're just going to expand on it a little bit. So here is that same example using an x and y and mapping to a z. And so over here you have your domain there on the left, right here, and it's mapping over to different individual values in the range of z. Okay? And that's just a nice little diagram for it. So normally, the way all these kind of mappings work is you have some domain, and then over here you have something called, so this is the domain, and this is called the codomain. And then inside the codomain, you have the range, and the range, I guess, could be entirely the same as the codomain, but it doesn't have to. And the domain maps to values inside the range that is inside the codomain. And so, we can see something like that mapping over. All right. Here we have these functions of two variables, and you can see what we had before. Now instead of z, we just wrote a y in. So w equals the square root of y minus x squared. The domain is everything such that y is greater than or equal to x squared, because other than that, you end up with a negative square root, and we're getting into numbers that are no longer real. And so therefore, we have a range of going 0 to infinity, and you can see these. And then below that, we have similar functions, but of three variables, x squared plus y squared plus z squared square rooted. We can put any numbers we want in there. They're not going to give us any negatives, because anytime you square them, they all become positive. So it's always the sum of three positive numbers there. And, take a look through those. Next, another definition here. We have a point x naught, y naught in a region or set R in the xy plane is an interior point of R if it is the center of a disk of positive radius that lies entirely in R. A point x naught, y naught is a boundary point of R if every disk centered at x naught, y naught contains points that lie outside of R as well as points that lie in R. The boundary point itself need not belong to R. The interior points of a region as a set make up the interior of the region. The region's boundary points make up the boundary. A region is open if it consists entirely of interior points, and a region is closed if it contains all its boundary points. So let's take a look at this. Here is an interior point. The idea is essentially what we're doing is we're looking at a single point, and then we're looking at, now they kind of make it just any radius of any size, but it can be super small. So we could essentially be looking at all the points that were just surrounding it, right? And so if you look at all the points that are just surrounding it, each one of those points is actually inside our region, and therefore the main point we're looking at here in the middle is also therefore in the region. But if you come down here to one like this, you look at our main point in the middle, and then you look at all the points around it, that surround it, and you see that these ones over here are not in the region. And so it contains points that are on this side that are inside the region and this side that are outside the region, and therefore that is a boundary point. Okay, that's what essentially is the way we're looking to see if it's a boundary point, is whether or not all the points around it are inside or outside. The way I think about this is I think, all right, let's say I had here's a thing of water, and I could have a water molecule right here that's on the edge, and then above it is air molecules that aren't a part of the water, and below it are water molecules that are a part of the water. So water, air, like that. And so I know that that is a boundary. That's a surface particle of water. Whereas if I look here and I look everywhere around, right, that single water molecule, all the other water molecules is all that's around it. It's all water molecules that are part of that water, and therefore that is actually an interior bit of water. It's inside the bulk of the water and not on the surface of the water. So similar kind of thing or way of thinking here. Here you can see we have an open unit disk. Every point is an interior point because we only contain the interior points. We're not looking at the boundaries. Here we have a boundary where all we're doing is doing the collection of points that count as boundaries. And then we have a closed unit disk where we contain all of the interior points and the boundary points together. So this is ignoring, like there's not an or equal to. Notice that missing there. Here is just equal to, so that's just the ring, the outer boundary. And here is less than or equal to, so that includes both things. All right, definition here again. A region in the plane is bounded if it lies inside a disk of fixed radius. A region is unbounded if it's not bounded. Okay, so I mean that's pretty much what it says. If it's bounded, it's bounded. If it's not, then it's not bounded. So here we're going to describe the domain of this function. We already did a couple pages back where we need y to be greater than or equal to x squared. That's our domain there. We have the or equal to, so we would have a boundary on that one with our or equal to if we were thinking of it that way. Okay, here we've got the same thing. We have the interior points where y is greater than x squared. And then we have the actual boundary, which is the parabola where they equal each other. And then we have outside, where we're not getting any values, and we can't have it be true. And so this is our basic thing, is we are everything inside of here, and stuff outside would give us unreal answers, imaginary answers, complex answers, whatever you want to say, and therefore are not part of it. All right? Yep, another definition. Here we go. The set of points in the plane where a function f of x has a constant value, f of xy equals c, is called a level curve, all right? And I'll show you in some pictures here in a second what exactly that means. The set of all points, x, y, and then the actual output of the function in the space of the domain is called the actual graph itself. The graph of f is also called the surface. So z equals f of xy, which is what we were looking at in the last chapter, or was it chapter 4? Anyway, we were looking at curves. And then here we go, we have this level curve. So let's take a look here. Essentially, what we're basically doing to get a level curve is we're holding the z value constant, right? We're coming over here where we're holding the z value constant. So that's like taking a plane, say this is the plane z equals whatever, z equals 10, right? And then what it does is it's going to intersect our surface, create a surface, create a line, and then we can drop that down into our xy plane, and when you drop it down there, that's our level curve. All right, and so you can see they've done that with a few of them there. They've drawn out a few different level curves for specific values of z, okay? And that's essentially what they're doing. They're projecting that value down onto the xy plane. Here you can see that picture a little better, probably better than I was drawing it. There's the z equals 75 plane. You can see it intersects, makes this circle right there, and then you drop it straight down. There's your level curve. This is a contour of it right here. For when z equals 75, this is the level curve right here in the xy plane, like the shadow of it, the projection of it all the way down. So you're like projecting it down onto there. Okay? like that. Here is a nice little just example of a contour map in a regular old topological map, and you can see they have all these curves, and each one of these curves is representing a certain value for height. So you might be able to look at this and say, all right, this is 100 feet, this is 90 feet, this is 80 feet, and then everywhere you go around this line, you know, oops, I got off of the line. Everywhere you go around this line, you know you're at 80 feet. And then this would be like 70 feet and so on and so forth. And you can look at this and tell things like it's very steep over here where the lines are really close together, but here where they're farther apart, you know, it's not as steep right there. Okay, so not as steep. And so you can get a lot of information about this, where this might be like a really steep place you'd want to avoid and not try to climb up. Through here, it's not so steep. It's taking a longer distance. So, you know, if this was 10 feet here and this was 100 feet here, it takes that whole distance to go it, whereas this goes from, you know, 10 to 100 in a very short distance. It's very steep. Okay? So just a little example there. All right, another definition: the set of points x, y, z in space where a function of three independent variables has a constant value. F of x, y, z is equal to c is called a level surface. So instead of a level curve, we have a level surface now that we've moved up to a higher dimension space. So here you can see our level surfaces, and we have functions of x, y, and z, and then they equal, you know, w or whatever you want to say. And so we have these contouring different surfaces that occur when it equals different constant values right there. So this is like, you know, four-dimensional graphing here. Here you can see we're extending the same thing out to interior point to a point that is surrounded by all other points that are inside your region, and then in boundary point is a point that has surrounded by some interior region points and some points that are not inside your region. So similar thing, except three-dimensional now. Instead of a circle, it's a boundary sphere. So we're looking at everything around it in a spherical shape, all around it in every direction, and looking to see if it's a boundary or interior point. So a point x naught, y naught, z naught in a region R in space is an interior point of R if it is the center of a solid ball that lies entirely in R. A point x, y, and x naught, y naught, z naught is a boundary point of R if every solid ball centered at x naught, y naught, z naught contains points that lie outside R as well as inside R. So that's what we were just talking about on the previous page. The interior of R is the set of all the interior points of R, and the boundary of R is the set of all the boundary points. A region is open if it consists entirely of interior points. A region is closed if it contains its entire boundary. All right, so very similar to talking about before. Here is a nice little graph showing you this three-dimensional kind of a graph going through with different curves and stuff. Here are some more of them. You can see the actual three-dimensional graph and then the contours down below it. Again, these are just x, y, and z functions, so they're three-dimensional. You can see that, of course, in the combination of these two pictures above is helpful. This right here, unless you actually define things like these are like that contour map, unless you actually define what height each of those are, I mean, you can't tell if it's this picture up here, or maybe this one was pointed down while this one was pointed up. You can't really tell that from the bottom picture without more information, or they both could have been down like this, like they could have been pointed in the other direction. But you can't really tell that from that picture unless you went through and started saying like, this is 10 and this is 10 and this is 9 and 8 and 7, 9, 8, 7, so on and so forth like that, unless you actually put numbers or values on each of those to tell where they are. Okay, because it could be something like positive 10 and that could be at negative 10, where this is a peak and this is a hole or something like that in the ground. Okay, so we can't really tell without those numbers on there. So there's some limit to those pictures there below, but it does give you an idea about the contours. All right, And that's pretty much it. Next time we'll go on to 14.2 and start working our way on forward. Okay? Thanks a lot.